A mass driver on the moon is what will let us grow our space infrastructure to scales that look like science fiction today, because it would let us en masse to low Earth orbit, medium Earth orbit, geostationary orbit, or anywhere else there's demand using only electricity. A solar-powered first stage with effectively instant reuse, capable, in principle, of throwing tens of thousands to even hundreds of thousands of tons a year into space. This is not a new idea, it's old news. People have been talking about this since the 1970s, most famously Gerard O'Neill, author of The High Frontier, and the mind behind the O'Neill cylinder. But as impressive as those giant habitats are, future generations may remember him even more as the father of the mass driver, that crucial piece of infrastructure which makes everything else possible. O'Neill understood that a lunar mass driver was the linchpin on which our future in space swings. With it, you can do almost anything. Without it, you're stuck with rockets and the hard limits of chemical energy. So, in the mid-1970s, he started building hardware, and by 1976, Mass Driver 1 was done, the first space launch coil gun prototype. It was, well, not great, but that's fine, it was a first-generation demonstration. Then he built Coil Gun 2 and Coil Gun 3, with each generation having major improvements over the last and setting new records. From the beginning, though, O'Neill's ultimate vision was a superconducting system. Conventional coil guns suffer from eddy current heating in the projectile coils as you push toward orbital velocities. Past a certain point, you just melt your armature. Superconductors solve this killer problem. They can carry enormous currents with no resistance. So you can reach much higher magnetic fields in a much smaller package, and you can, in principle, move energy around with very little loss. O'Neill's long-term plan was a launcher where superconducting coils, at least in the projectile and eventually in the track, would let you build a much more powerful, compact, and efficient mass driver than copper or aluminum coils ever could. But O'Neill was never able to actually fly a superconductor. He did test them on the side for coupling, but he never launched one, and unfortunately, in a pattern that is all too common, in 1981, NASA shifted priorities and cut funding for the mass driver studies. But that wasn't the end of coil gun research. In 1982, the year after O'Neill's experiments ended, the Department of Defense funded the University of Texas and Sandia National Laboratory to research electronic launch systems. Long story short, they spent a decade developing a linear induction motor, which would go on to become the EMAL system used on modern aircraft carriers, but the eddy currents were too severe at higher speeds, so they went back to DC induction systems similar to those of O'Neill, but with better electronic hardware now that it was the 1990s, and after building the fastest coil gun ever, at least publicly, up to 1 kilometer a second, they decided to go the superconducting route since the projectile was heating up to about 450 degrees Celsius. And if they pushed on to orbital velocities, then the projectile most likely would have melted. So actively cooled superconductors made sense as the next step, just as it had with O'Neill. Then, right when they were about to start testing superconducting coils, priority shifted and funding was cut, and research reoriented towards development of the railgun system. And then, very little happened for the next 20 years. Until now. Ladies and gentlemen, nearly 50 years after O'Neill's mass driver experiments began, I am extremely excited today to talk with David Dillon from Electromagnetic Launch, who, together with his team, is taking up the mantle and working to develop a high-temperature superconducting quench launcher that aims to realize that long-imagined design that earlier programs never quite got to finish. My hope is that by the end of this conversation, you'll see why this third wave of work on superconducting launchers deserves to be taken seriously. It's very nice not to have to explain why we should even go, just starting from that already common ground.
I don't know why people don't get it in the sense of why wouldn't you be interested in unlimited raw materials? The solar system, at least at a human scale, is unlimited raw material. Why wouldn't you care about that? Or unlimited energy, at a human scale, it's unlimited energy. You'd think people would be interested in that, but not. So anyway, some are.
Right. They think you're crazy until they start benefiting from it. Like the internet, people would think that's crazy, and now it just came out of nowhere.
Right. Yeah. Well, some years soon, I think there's going to be greater interest in all of this.
Mm-hmm. For sure, yeah. And all this stuff that's happened with SpaceX has moved the needle a lot, and just in general, There's a lot of moment. I mean, I remember I started talking about the moon publicly 4 years ago, and it was like I was screaming into a void. And now there's a lot of people starting to talk about it. It's starting to get a lot more respected. So
Right.
that's good. Yeah. And I won't go too hard on the moon. We could just talk about the system in general. We could talk about its use cases on and off world. I know you're very focused on like the Earth at first, right? But
Yeah.
we're really just developing it.
I mean, the truth of the matter is, mass launchers is a pretty broad field and a really old field, right? I mean, I don't know what the first one was, but it might have been the sling, and it's just stepped up from there, through technology and over the centuries. And so with all these different applications, there's more than one Earth-based. There's certainly our first love and interest is in launch to orbit, but there's lunar applications, and then there's Department of War, DOW applications. There's a lot of reasons or a lot of applications for putting a mass driver to work. It just happens that I think we got introduced through the Planet Sunshade Foundation project. So, but other than that, lunar for us is just one place, and their project is just one reason to be carting raw materials around the solar system. So,
Right.
and with that, since there's such a range of things to do with mass launchers, I do want to talk a little bit about rail guns and coil guns and kinds of other approaches. In some ways, I hate raining on other people's parades because go get them. I want them to succeed. And I'm sure there's an application somewhere that was a good fit for a coil gun or is a good fit for a rail gun. But I think it's a helpful way to start in a description of what we're talking about to sort of explain what the roadblocks are that this is a solution to. So I'm not saying there is no use for a rail gun or a coil gun in this world, but not for very high velocities and very large masses for reasons I can explain.
So what basically convinced you to invest your time and money in this technology in the first place?
Sometimes I think an idea picks a person rather than the other way around. The truth of the matter is I was writing up patent stuff for a business that we started and then sold, called Verify Brand, and it was an anti-counterfeiting business. And I was writing up patents just to save money, because if you write enough of it, the whole cost goes down from a legal fee standpoint. And for years, I'd had thoughts about electromagnetic propulsion and why doesn't it work and who isn't, and I would search on the internet and look for things and not find things. And I finally decided to write up this approach and filed it along with all the rest of them. I think there were maybe a dozen or so all involved by the time it was done. But this one was not, it didn't have anything to do with anti-counterfeit, but surprisingly enough, I ended up getting the patent. And truthfully, the patent is not significant in the IP of what we're doing, but it started me on a journey to talk to other folks about why doesn't this work, which started with a guy who was Graham Candler. He's at the University of Minnesota, brilliant guy, nice guy. And he was really relatively generous with his time. I called him and said, you know what? I'm interested in this subject, and I'm guessing that maybe your area of expertise is why this doesn't work. Graham is a national expert in hypersonics, and a lot of folks use his code, which looks at the effects in hypersonics, even right down to the level of what happens to some of the chemistry that's at the leading edge of that problem. And would you be willing to talk to me about it? And he was. And I went over to the University of Minnesota and sat in his office, and we talked about it. And he says, look, I don't think hypersonics is your problem. You need to talk to the folks at the University of Texas in Austin. They're the ones who really worked on this. And he made it an introduction, and the next thing you know, I'm down the road driven by my own curiosity of, okay, why won't this work? And so that was really the genesis of it.
That's awesome.
Yeah.
And then from my understanding, your system uses high temperature or regular superconductors, or you're working on both?
High temperature superconductors. I'll get more into detail on that, but as long as you've asked, for your audience, one of the dirty little secrets about high temperature superconductors is that they actually like it being really cold. This idea that you can run at liquid nitrogen temperatures, yes, that's technically true. But if you really want to get a lot out of your high temperature superconductors, they like it colder, 25 Kelvin, that kind of thing. So,
I guess, they just have higher Curie points, but like it's still better. Colder is still better even with them.
Right.
They're just less sensitive.
Yeah. There's some other stuff that gets pretty geeky too, having to do with how they reject magnetic fields, but they're clearly the way to go. And so, when we went down to Austin to have a first meeting about this, and people who had worked on it came together, and there was a conference, and the discussion on railguns became the first thing, because these folks were involved in the original railgun research effort, Harry Fair and Mehmet Erengil and others. And Many tens of millions of dollars were spent on research on railguns back in the day. This goes all the way back to, Ronald Reagan and Star Wars and all of that. But, and you've talked about it in your own videos, the core issue of low efficiency is a bad place to start from. I mean, it's just the fact of the matter is you're starting out in a hole, and it's the kind of problem that if you don't like it, and you're going to have to take it up with God, because this thing's going to be in the 30% range no matter what you do. And so, as I say, you're sort of starting out in a hole, and then you talked about the where problem. And there have been a lot of people that have tried to take on these issues over the years. I met a physicist who convinced himself, and maybe still believes, that if you brought the power in at the sides of the rail instead of from the bottom, with each individual power source having its own finger, that you would individually power, pass current across the rails through the armature and through the Lorentz force, send it out. And built his own with his own money, and I watched a video of it. It was like a spark factory as this thing went up. And it just wasn't a solution. And at the end of the day, talking about the where problem, it's not trivial in the first place, in the sense that you can say whatever you want about physics and engineering and everything. It's economics that will rule the roost at the end of the day. And if you've got where, whether it's refurbishment or replacement, you started out at low efficiency, now you've added economic problems to the thing, to the point where, it's in deep trouble. And then you didn't mention, and I kind of wish you had in your video, maybe the most serious problem, which is, if you believe that there's going to be any wear at all, no matter how well you've managed it in the world's best wear-resistant, super slippery materials and multiple rails stacked up on, so each one has to do a little bit of the work, and all the things that you might do, there is going to be a little detritus that's going to come out behind the armature as it moves. And when you let that conductive detritus, that dust, come out behind the armature, you're going to get a restrike. And it's going to draw current out of the system. And the harder you push current into it, the worse this whole thing gets. That's kind of what they finally figured out from a physics perspective, was that the harder you tried, the worse it would get. And that's built out of the low efficiency problem, out of the wear problem, out of the restrike problem. The DOD ended it. They cut off 100% of the research and said, we're not doing that anymore. And it turns out these guys had other ideas. But once you've laid a $200 million egg, it's hard to get people to listen to you about that.
Right. So for them, I encounter this problem a lot where we'll be talking about mass drivers, and then we're talking about two different contexts, on the moon versus on Earth. And I agree with you. I think for the Earth, even if there's a very little amount of ablation, or even if there's no ablation, the efficiency is a lot more of a concern. On the moon, you can deal with these things a lot easier because you don't really need an enclosed tube or whatever.
No, but the restrike problem would be worse or as bad in the vacuum of space. As the detritus comes off from what created the wear in the first place, you're going to be running a little arc welder up your rails.
Right.
Anyway, so that was an approach, and the group felt that there was no chance that was ever going to get anywhere because of what they would call non-trivial physics problems. And then, next came along this idea of, well, let's use coil guns. Well, what we want is a high magnetic field, and what the world now knows. And it's funny, in each of these cases, there's somebody who's still pursuing it and pouring money into it, and yet we kind of look at it and shake our heads. What Ron Kay at Sandia Labs took this on around the year 2000, spent millions, and showed what it is about it that makes it like a dead end from a physics standpoint. The issue is, if you've got a copper coil or an aluminum coil, or what people would call an ohmic coil, a coil that, a metal coil that has resistance on its own at normal temperatures, the harder you drive current into it, trying to create a bigger magnetic field, the hotter it gets. And it's one of these problems that feeds on itself. And the harder you try, the worse it gets. And the more resistance you get, and the more resistance you get, the more heat you get, the more heat you get, the more resistance you get, and you're off to the races. And that alone is a major problem, but it's hardly the end of it. And as I think you know, and some of your folks know, the magnetic reluctance, the resistance of the magnetic field itself is a problem. And I think it's worth taking a minute to kind of back up and talk about something kind of fundamental about electrons and electricity. And a lot of your audience was taught in school, as I was, that electricity is a bunch of electrons whistling down a wire. And that's just not true. I mean, it's not even close to true. First of all, electrons aren't a bunch of little particles like little BBs. And, the idea that electrons are excitement in the electromagnetic field and energy excitement at the smallest possible unit in the electromagnetic field was something that we weren't ever even close to being taught. And the other thing is that the electrons that go down the wire, they're moving at the pace of a snail. I mean, literally, that's slow. And yet, as soon as those electrons move at all, instantly comes the magnetic field. And that whistles down the wire at the speed of light. And having that different mental model, I think, helps you understand the second problem that coil guns just can't get out from underneath. And again, it's magnetic reluctance, right? The magnetic field itself provides the resistance to the flux. That's what flux is, what people call magnetic energy. And so this is another one of these non-trivial, if you don't like the magnetic reluctance problem, you're going to have to take it up with God, because there's not an engineering way to make it go away. And it turns out that, the formula for the math formula, if you look at, where's the magnetic reluctance, how's that calculation made? It's a length time divided by cross-section kind of a calculation. So you end up with this idea that the smaller wires, which might give you a better solution, well, but those are the same ones that you burn up when you pour a lot of current into them. So it's a really difficult problem. And if that wasn't enough, and it is on its own, without having any other problems, you end up with all these banks of capacitors or ultracapacitors, and that's a problem. And then you say, well, but that's not a problem. I own a capacitor factory. And it's like, okay, but you still have the switching problem where you have to dump all that power in, just at the right time, exactly at the right time. And the exactly the right time, space of time goes down as you go faster. And so, there's an old saying you only need one nail to hold a coffin lid shut. Well, a coil gun's got about 4 of them. And it really was run to ground by Sandia Labs, and we know it can't work. And yet there's an organization today that's a spin-off from the folks that had the spinning system, where they would throw things up into orbit. And, they skipped the physics part and put a big investment into a control room that looked like it belonged on Star Trek. And some of those same folks now are still pushing coil gun stuff. And I don't know, we looked at all of that, and some of the physicists involved had a different approach. It was to follow in the footsteps of Henry Combe from MIT, which people call a quench launcher. And once it kind of got on a blackboard and I got my head around it, it was like one of the guys involved, Jerry Parker, said, well, I don't know if this can work, meaning electromagnetic launch, but he said, if it's going to work, this is how it's going to work. And finally, the pieces kind of clicked together for me, and it became a bit of a passion for me. And I've been talking to people about it ever since.
Right, and Colm worked with O'Neill, like he was on the original mass driver.
Yeah. And I think Jerry O'Neill probably fired the imagination of a lot of us from back in the day. We grew up seeing the O'Neill cylinders and NASA's first Apollo launches, and we figured all this stuff was going to come together. And the truth of the matter is, it can't with rocket economics. I'm as big a fan as there is on the planet Earth with what Elon Musk has accomplished in his life in general in the first place, but with SpaceX and reusable rockets and their approach in the second place. But if you want those kinds of things that Jerry O'Neill was talking about, taking $10,000 a pound for launch to $1,000 a pound, thank you very much. And $1,000 a pound clearly can become 700, 500, 400. I don't know how low, because the number of reusabilities is a bit of a debate point, but it's not going to be $4 a pound. If you really want to get to low cost, the electromagnetic launch, particularly it has to be repeatedly reusable, right? Otherwise, it doesn't help, is the correct approach. So, we ended up looking at all of this and saying, all right, our high temperature superconductor quench launcher makes a lot of sense. Now, the first thing is, if you want to pull on something really, really hard, pull or push with a magnetic field, you're going to need an enormous magnetic field, right? I mean, it's sort of obvious, but you got to get it said. And it turns out, from a structural standpoint, it's way better to pull on things than push on things that are high length, small diameter things. It just, tension works better than compression for that kind of stuff. But the thing is, really high Tesla field strength, that comes from current density, not just current. We talked about that a little bit before. If you made, you say, just my example is I want to use 500 amps. The current that would run 2 entire houses flat out, that's what I want to use. And I'm going to put it in a wire, this big around and make a coil out of it. That's not much current density. And you're not going to get a very big magnetic field. And if you start shrinking down that wire, if you will, you get to where we are with a quench launcher where it's the size of a human hair. It's like, imagine if all the power in your house was in the wire strand that runs your Christmas tree bulbs. And that's the kind of current density we're looking at. And that's what creates these huge magnetic fields. And by huge, just by way of example, these high temperature superconductors are being used to squish things down to fusion levels of pressure. So it gives you a sense. We don't use that high of a Tesla field. We don't want to. It would break apart our launchers, and we can get where we want to go if you run the numbers at way lower Tesla fields. But the point is, it takes you well past what's available in coil guns, I guess. And then, if I'm going to talk about how ours works and how actually a quench launcher is a bit of a misnomer, but it's a name that's stuck, and I'm not trying to re-educate the world on names. I think it's worth taking a minute to talk a little bit, just like we digress to talk about electricity, what actually happens inside a superconductor.
Before, if I could just interject, I just wanted to say, regarding what you were mentioning about eddy currents and coil guns in general, I just want to clarify that, these things, they work fine on small scales, but it's very hard to intuit the energies involved in going 1 kilometer a second. And for the moon, we need 2.4. For Earth, we need 9.4 to 11 kilometers a second. And so that's when you really start getting this melting effect and all of these problems that you mentioned.
You're really right. I actually haven't mentioned eddy currents yet, but we can talk about those. If you said, well, make a list of things you really worry about, it's like, well, we'd put eddy currents on the list.
Well, that's what causes the heating and the ohmic heating. It's not just eddy. There's heuristic losses, but in general,
Yeah, and so at one point early on, we had folks saying to us, you really need to build this into a computer model, and then we can run it and show different things and go show it to people. But it didn't take too long to figure out, to your point, you have assumptions that are in your computer model. Well, are those right or wrong? And when you get to the higher speeds, how are you going to know? And really what it came down to is we need to build a physical subscale demonstrator. We won't have anything that's impressive enough from our own perspective. Impressive is maybe the wrong word, but we need to show it in physical reality. That gives you something that you can then model. So, or to put it another way, we won't really know what we're doing until we start blowing up more stators and switches. That's right. That's how you find out where the edges are. And there are practical problems at the higher speed. Maybe you don't need to go to 2.4 for the moon. Maybe 1.8, 1.9 puts you in an orbit that from there things get transferred. There's it doesn't take much from a rocket motor standpoint to change your delta V from 1.9 to 2.1 to move it to some other location. Same is true with Earth, right? I mean, it's probably unlikely that we would get to the kinds of velocities in Earth launch where you could literally do it with no rocket motor assist. But if you can get it down to just what people think of as sort of a third stage size small rocket motor, again, the issue is economics, right? I mean, we're not Puritans about this. We don't have to do the thing the whole way, electromagnetic launch. If you could get, I think we used 5.6 kilometers a second for a lot of our economic analysis. So that takes off, everybody's heard about the tyranny of the rocket equation. Well, it turns out the thing's kind of pyramidal. At the bottom, it's horrific, where all you're doing is burning fuel to lift a whole bunch of fuel about 2 inches. And up at the top, it's not so bad. And so I think rocket motors are necessary for delta V and circularization. But also, orbits are shared. And throwing stuff up onto orbit out of control doesn't seem like something others would accept. So a little bit of control is necessary anyway. But
you probably even need that for the moon. Despite the fact that there is no atmosphere, you're still going to need a kick stage for circularization. orbital. I mean, yeah, it's hard to escape that, but we can reduce the cost by significant margins by using what is essentially like an electric first stage, not in the way of like an electric battery charging the turbo pump or whatever, but like you're literally taking electricity and using it, turning it directly into kinetic energy. So it's like an electric first or second stage. I call it like assuming you're using solar power, which you could use nuclear or whatever, coal. But if you're using solar power, it's like a solar powered rocket, more or less. It's tongue in cheek.
Yeah, no, but I mean, that's exactly right. You have to always come back to economics rules the roost. What are you going to do about the economics? And otherwise, we'd have O'Neill cylinders right now, but economics don't work.
Right, and it's telling that that's what O'Neill invested his time. I mean, everyone knows him for the cylinders, and he drew those drawings and he talked about them. But what he spent his time doing was trying to develop a mass driver because that he knew that was kind of like what unlocked everything. It's so important to.
Yep. And Henry Combs was absolutely on the right track with the quench launcher and superconductors. There weren't high temperature superconductors back then, but it's what gets you to these high magnetic fields, and you're going to need those if you're going to push like crazy or pull like crazy on something to get to the kind of velocities that we're talking about, particularly with amounts of mass that matter. You'll see some demonstrations, and they've managed to launch a poker chip size piece of plastic to a high velocity, and that's like, well, that's not what's needed here. And before we sort of dive into the how does it work and all that kind of stuff, I just thought it might be useful for people to know, because it'll come up in the explanation of how our approach to this works as to what's really going on inside a superconductor. We talked about those electrons before, but it turns out that if there's a particular atomic lattice, which is actually very hard to make, the raw materials itself is cheap, but putting them down in such a way that you get the atomic structure you want makes them very expensive. They're coming down in price because there's so much of it made now, so that's good, but makes it very expensive. And that atomic structure combined with really low temperatures, right? Liquid nitrogen is kind of where it starts, but they're happier at 25 Kelvin, that kind of thing, causes two electrons to form a Cooper pair. And these are things that we would normally expect, well, they're going to repulse each other, right? They're both negatively charged, so that's not going to work. And that's the miracle of a superconductor, that they can force these electrons together and they form what people in the business call a Cooper pair. And it turns out there's a property for these particles, I use the term advisedly, of spin. And of course it has nothing to do with something spinning, right? It's one of the numbers that's in the equations describing what's going on. Well, it turns out that if you have fractional spin numbers, then you're a fermion, you're like most of the ordinary matter in the universe. But for those unique ones that have single integer spin numbers, like 1, you're a boson. And so the universe breaks up, the normal universe, material universe breaks up into mostly all fermions with these specialized bosons running around. Well, Cooper pairs become bosons, and when they do that, they get to violate the Pauli exclusion principle. Two of them can be in the same place at the same time. It just falls out of the math that describes how electromagnetic things work. And sure enough, it's true. And so that's how it comes to be that enormous levels of current can flow through a wire the size of a human hair. So the thing about putting those crystals or those atomic level structures together that can force Cooper pairs together is that they're easily upset. There's a number of ways to upset the apple cart, and we can talk about that a little bit. But I suppose maybe the first thing I should share is that the reason the quench launcher is not an apt name, but it's what everybody calls them, so we use it, is because we don't actually quench the superconductor. So probably what I should do is start with a description of it. It's a vacuum tube. Don't need a vacuum on the moon, but it's a vacuum tube. And there's stator rings every so often. So if it was a 1 meter tube, probably every 1 meter or so you'd have a ring. And inside that, there's a carrier sleeve that itself has a high temperature superconductor wrapped around it in a closed loop. So it's just a continuous current that goes around and around. And inside that carrier sleeve is the delivery cylinder. And it can be of whatever you're interested in doing. It needs to accept high G forces, 80 Gs, 100 Gs, more. So no people. And these are smaller diameters, like a 1 meter diameter, 1.5 meters kind of thing. And there's a reason for that if you want to go back and talk about it. And And so raw materials, liquids, roll stock, powders for 3D printing, liquids for water's an example, fuel's an example, and they can go on the delivery cylinder. And it's really important that the delivery cylinder be made of something that's useful on orbit, because it brings us back to the economics. So we've done a fair amount of work, and it's at issue right now in the Planet Sunshade Foundation project, that the delivery cylinder in that instance should be lunar regolith derived, that it have economic value on orbit. Best if it was directly usable, but if it could be upscaled to something else, or if need be recycled to be useful. But if you want the economics to work, you don't want to be throwing away those cylinders. So what happens in actual usage then is that as the carrier sleeve is pulled in first into every stator, the current goes to zero as the carrier sleeve gets to the middle. What you've done is you've changed the magnetic energy in the stator to kinetic energy. And it's actually an old idea, right? I mean, if you didn't do anything after that, as the carrier sleeve would leave, it would regenerate that current and pull it back. And it would go back and forth. And you'd have a very expensive giant doorbell instead of a launcher. So the initial realization was that as the current goes to zero, we've talked about the switching problem with coil guns and other things. Well, zero is a heck of a good time to be doing your switching. And so we developed some technology around switching. It combines high-speed electronic switches. For those of you in your audience are familiar with them, there's like modern MOSFETs that do just really great job of very high speeds and pretty darn good voltage standoff. But we've combined them with physical switches, contactors, so that they each play the role that they can. The MOSFETs give us the speed, and the contactors give us the very high voltage standoff where we run. Because as this thing leaves, particularly as you were saying earlier, at the higher velocities, enormous currents are attempted to be generated. And so that's our first bite at the apple. But there's a second piece of this. It came from work that was done quite a long time ago, really, having to do with pulse power applications. So I was saying it's very easy to upset the apple cart of a superconductor. And you can, right? If you raise the temperature, it doesn't want to superconduct anymore. And that's a quench event. And if you run too much current into it, as much as you can put in too much. If you bypass that if you go past that critical current, you'll get a quench event. And one of the physicists who worked on this, he was taught when he was a student, his instructor explained the amount of energy that would be unleashed in your quench event in fractions of sticks of dynamite. So they would be understanding what they were dealing with in the lab. So you can unleash it that way. You can ruin or upset the apple cart in terms of the structure that's necessary to hold these Cooper pairs together with just too much magnetic field. So there's all these different ways to do it. Well, there's another way to do it, which is with radio frequency. You can pound on a superconductor with electromagnetic radiation, presumably radio frequency, but it could be other frequencies. That upsets the apple cart. So if you do something to a high-temperature superconductor when there's no current in it at the 0 point, it begs the question, is that a quench event? And it's like, well, that's a semantic discussion that people can have, and say what you will. But technically speaking, we see a lot of benefit from coming from never quenching in the classic sense, when there's a whole lot of current and then you stop it from being a superconductor and the current's got to go somewhere. In our case, where the current went was into kinetic energy, pulling the carrier sleeve forward. So, that's kind of it in a nutshell. That's what we're doing. That's what we're on about. We're in now in various conversations with folks about building this demonstrator, this subscale demonstrator, and I don't know. It's gotten pretty exciting. Our patent stuff has gone forward, so it seemed like a good time to rather publicly talk about not just what we're doing, but how we're doing it.
Right. When do you think? What are the timelines on this? When do you think you'll have I guess the building the hardware will start, and then when we might be able to see the first prototypes and results? Do you have timelines on this? I guess years or?
from start to a subscale demonstrator, we've mapped out as 18 months. Start date isn't certain at all. My hope would be that we would start this fall. So maybe just in a year.
Awesome.
Yeah, but it's rather mapped out as a project. 18 months. It would be a subscale demonstrator. It's a demonstrator that would run in a lab, which is necessarily has to be safe. So there's certain restrictions on it in terms of energy levels and other kinds of things that you can imagine. But that gives us the data to model it. Basically, what we've done is shown the physics and proved the engineering. And then the next step for us would be a mid-scale demonstrator. And that has to either be in a specialized facility or a firing range.
Right. So subscale would be probably late 2027, early 2028, and then from there you would go mid-scale firing range, and that would be somewhere 2030s-ish.
Right.
2029.
And
That's
taking
awesome.
a page out of sort of the Elon Musk thinking, my hope would be that once we've shown enough on our way to the subscale demonstrator in terms of showing the physics and proving the engineering, that we could concurrently get going on a mid-scale. There's no reason to wait until you're done with one thing to start the next thing if you've shown enough of it back here. And the whole idea is to collapse the time frame into faster.
Awesome. And you've talked to these guys, Colm and...
No, I never did.
Fair.
Harry Fair knew Henry Combe, and Bill Snow worked with Henry Combe, but I never had the pleasure of meeting him. I wish I had.
Okay. Well, I mean, you've talked to these guys in general, the industry, and you know the history of this. And so I was curious, from your vantage point, what was sort of missing back then that made it harder, besides, I guess, the funding cuts and things like that? Is it just superconductors needing to be developed more? Or are there other things, electronics, you mentioned the MOSFETs, modern MOSFETs and switching. Is there anything else that that most people probably don't realize that kind of held back this technology? Because it's been about 50 years, 45 years, I think, since O'Neill first started. And so... Yeah,
well, maybe not that far, but Harry could talk to you more about that, as could Bill Snow. The way I think about it, Henry Combe didn't conceive of a completely done, finished project. What he understood was a direction to go in. The superconductors would give you the really huge magnetic fields. And then it turns out superconductors also have the ability to collapse in their ability to be a superconductor, which in itself is a switch idea. And so he saw a correct direction where you could get enough energy to put to work and where you could collapse it or stop it. There wasn't a detailed working system. And that's, I don't know, a lot of ideas can sit around for a long, long time. And, I don't think the people that started working on railguns back in the day were dumb. I think they were smart. They recognized they didn't have any solutions to the switching problem at all. It just physically didn't exist. They didn't have high temperature superconductors. So they went and did what they could do, One big giant Frankenstein monster switch, boom, throw it down and pour all that current into your rails, and it worked. And then from there, it was just engineering to try to get rid of the problems until they realized, and that's what, as I say, Harry Fair and Jerry Parker and Mehmet Erangel and these other people worked out, was the physics problems were not going to get resolved. And you can't engineer your way out of the fact that it's low efficiency any more than you can engineer your way out of the reluctance problem in a coil gun. So anyway, I guess it just took time for the more straightforward approaches to sort of be shown not to work, while at the same time new materials came along. New materials in high temperature superconductors. And even the early high temperature superconductors wouldn't have worked. They were too brittle. They didn't understand how to make them like they do now. A lot of what has made our approach possible is because of the hundreds of millions of dollars that have been invested in fusion. In a lot of ways, we're the byproduct. What we can now do is the byproduct of what's happened in fusion energy.
Yeah, have you seen this recent Viper cable? It came out from, I think, a university recently, and it's
very cool cable.
Solid.
Very cool cable. Yeah, no,
I immediately thought of your technology.
Yeah, no, and we've had the good fortune to talk with folks from Commonwealth Fusion and Novum Industria and other places. When people in the business, in the superconducting world, get their head around what all this is, they recognize this will work. What remains to be seen is how well can it work, right? So they get kind of excited about it. It's been nice to talk to some of those folks, and better and better and better high temperature superconductors are getting made, and at lower and lower costs. Because I don't know how many fusion projects there are around the world now, but probably a few dozen, and they all need superconductor cable.
Right. And it's great for so many things outside of fusion. I know that's driving most of it, but it's sort of similar to the coil or, mass drivers in general. It's sat on a shelf. It's super promising. It just, for whatever bad luck but
Yeah.
these two things, they have a lot of synergy. I guess, what sort of performance are you hoping to get in the near term or long term? I know Sandia, their coil gun, they got up to 1 kilometer a second, and it got up to 450 degrees Celsius, the aluminum slug or I guess it was a coil, but
Yeah.
y'all shouldn't have that problem. Are you aiming do you have like a goal in mind, like, 1 kilometer a second or 500 kilometers, or just whatever y'all can get?
5
Nice.
kilometers a second. Well, the numbers support that it can work. The technology supports that it can work. The economics works from Earth launch at 5. In terms of, a lunar launch, of course, as you were saying, it doesn't need to go that fast. Somewhere above 1.8, but probably below 2.5, works from a lunar launch perspective. It is problematic as you go faster, though. You find all of the serious problems are just staring right at you in the math. In the case of the speed, it's the v² problem. It's really, sadly the case that it's just a lot harder to go from 2 kilometers a second to 3 than it was to go from 1 to 2. It just sounds like, well, it's just one more linear, 1 more kilometer a second. But that's not how it works, because it's the v² staring right at you when you force times, mass times velocity squared. So it gets harder and harder, and you have to pour more and more current into it. You have to have bigger and stronger fields, and then you have less time. But we've got some things that help. You have 2 magnetic fields that are engaging. One is from the armature, and the other is from the stator. And they pretty much interact at the speed of light. So we've got one thing going for us that happens to go rather instantly. From our purposes, even a couple, 3 kilometers a second isn't fast compared to the engagement at the speed of light. But, we're going to have to build it to prove it.
Yeah, I guess I should have specified. I meant for your subscale system. Do y'all have like a goal for your milestone, sort of?
We do. And we've got a subscale system demonstrator. You can move up and down velocity and the weight from the standpoint of what you would build in the lab. But we've settled on, and I don't have the exact numbers in front of me, but a fairly heavy weight, meaning like 20 kilograms, bowling ball size. And one of the reasons to do that is to keep the velocities at, say, at a 200 amp, 300 amp level from getting to the point where they become dangerous. So, it'll be dangerous enough as it is, but to getting to the point where it's too dangerous, I guess I should say. So that leaves us at relatively slow velocities. I shouldn't try to remember numbers like this off the top of my head because I'll get them wrong, but it's like 80 or 100 kilometers an hour, or maybe even slower, maybe 60. The key thing for us in creating the demonstrator specification of what, as we run this thing, we want to be able to run it and run it and run it and run it and run it some more, and run it and run it and run it some more. And I think I maybe have told you this story before, but when Harry Fair went to a meeting at the Department of Defense with one of the generals, and once again they brought in a steel plate, and the general said, if you guys bring me another steel plate with a hole blown through it, I'm going to throw you down the stairs, because he knew the problem was that they could fire it a few times or 10 times, but that was not what they needed. And so there's a legacy of the old railgun problems bouncing around the DOD that has to do with the fact that they would wear out. And so it's important to us from a design standpoint for our subscale demonstrator to be able to run and run and run and run and run and run. It's an electric motor. It's a non-contact device. There's no reason, save our poor engineering, we shouldn't be able to run it 100 times, 1,000 times, 500 times. And we think that will be more impressive to folks on some different government department agency levels than the absolute velocity.
Right, yeah. If you could just dump mass in, and it can be small amounts, and it, accumulates over time to be big, very large amounts of mass, frequency. You don't necessarily have to be firing 1 ton every single time. It could be 1 kilogram 1,000 times,
Right. Although it turns out when you get into the math of it, that this kind of launcher scales nicely. It likes big and heavy. We can bring an awful lot of power to the game. And so there's really no reason for us to be thinking about launching 1 kilogram 1,000 times instead of 1,000 kilograms once.
What are the limits of it? Like are there structural limits or stresses that?
Yeah, I think that's exactly the point, the structural limits. As you scale out in diameter, the forces grow with the square of the diameter or the radius. So you can just and what you see is that once you go past a meter and a half maybe, you when you start squaring something, it gets out of control. You want to, because the magnetic energy goes up to the cube. So you're really paid off handsomely by going to bigger sizes. But at some point you tear yourself apart. And so, for instance, on that lunar launcher we were talking about, you'd like it to be as short as possible. But we specified, I think, 80 Gs as a maximum, just because if you're going to try to build most of this stuff out of lunar regolith, right, the superconductors themselves would obviously be shipped, well, I shouldn't say obviously, but would be shipped from Earth. They're lightweight and very hard to make. But a whole lot of the rest of this stuff, you would like to make it as much as you can out of, silica, aluminum, titanium, et cetera, the materials that are available to you at the moon. And it behooves you to try to keep the stresses low enough so that high precision alignment is retained over some pretty big forces. So diameter-wise, that's probably where we limit out. Length-wise, we're pretty tolerant. We can kind of go as long as we want, as long as the weights don't get crazy. And generally speaking, we either use, when we run numbers, water as a mass, just a number, or 3 times water for the mass.
Okay. What do you? I guess I'm not sure what you mean by that. Like 1 kilogram of or water as a mass?
Well, in the case of the lunar launcher, I wasn't sure if you were going to ask about that, so I brought some notes on it. But the internal volume of the delivery cylinder that we used turned out to be 5.2 meters cubed. We used 80 Gs for a launch velocity. For a stress, it got us to 2 kilometers, 2.06 kilometers of the length of, and that's pretty darn long, and maybe we'd be better off at 1 kilometer with a lot higher G load, but there's engineering analysis and that kind of thing. What Planet Sunshade Foundation was interested in is, does this work? Can this be done?
Okay, so you're starting with volume, that's why, and then you're just using the volume, and then you're using water as a placeholder for the amount of mass.
Right.
I see. Okay.
You end up with 6,000 pounds, at a crack. If you add in the carrier sleeve, which is again something that would have to be shipped to the lunar surface because it's a particularly difficult thing to make and it has to be reused, right? You got 17,000 pounds in mass total. So, and it just turns out that the B field strength to make that happen is 4.4. So well below what you can do with superconductors, but that's a lot. That's still a lot. And then but that level of field strength will give you 80 Gs on something that weighs 17,000 pounds. So, and so you start. The barrier is not what superconductors are capable of. The barrier is what the engineering can keep from breaking apart when you reuse it and reuse it and reuse it.
That makes sense.
Yeah.
Yeah.
So,
and then the Planetary Sunshade Foundation, they're working to basically look at creating basically it's at L5 or L2,
L4
disk,
is what they're talking about right now.
The disk that would basically block like 1% of the Earth's light to combat global warming, and using like lunar resources to construct that.
Yeah, and I should let them speak about that, because I think they're going to want to say what it looks like and how it would work and why it would work and all of that kind of stuff. Our piece of it is to be the freight train that brings raw materials to L4 is, I think, what they're thinking, Earth, Moon, Lagrange point 4, where you'd have 24/7 sunshine. So that's why they're looking at that place. And then it turns out the moon is just an awful place. As far as the moon is going to be for raw materials, that's pretty much all it's worth. I mean, everybody knows about the vacuum. A lot of people don't know that it's 2 weeks of sunshine with burning hot oven temperatures followed by 2 weeks of night, which way below freezing cold temperatures, I mean, I don't even know what it is in Fahrenheit. And in Kelvin, it's like 25, 30 degrees Kelvin, which is great if you want to make a superconducting launcher, but it's a miserable place. And then it's strewn with hyperabrasive regolith. You're knee-deep in abrasives everywhere you go. And if that's not bad enough, they're electrostatic. They want to stick to everything. I mean, it's just a terrible place. But as much raw material as you want, free for the taking. Titanium, aluminum, silicon, oxygen. Hopefully it looks like water. There's just a whole lot to be had in the way of raw materials there. But it's basically going to be a mining deal.
Yeah, I always call it a radioactive pile of slag. But it's our radioactive pile of slag.
And there's, for good reason, people are concerned and up in arms about hard rock mining in northern Minnesota because it's a pristine wilderness area. But there sits all this copper and rare earth and other kinds of stuff. All the rare earths you want without having to worry about hurting your pristine areas are right there and available free for the taking.
Yeah, right, exactly. And I know some people are worried that we're going to be like, when you talk about mining on the moon, they imagine you're defacing something that, we look up and we can realize that our ancestors, like people in ancient Egypt or Rome, looked up at that exact same untouched surface. But what they don't realize is that surface is constant. It is changing from asteroid impacts or meteorite impacts. And also the scales of the mines we're talking about, which could make these massive differences for quality of life and for our capabilities in space, are still so small you would have a hard time seeing them with a powerful telescope. O'Neill did.
That's exactly right. That's exactly right. But no matter what you're going to do, there are going to be naysayers who say, no, you should wear sandals and use candles, and that's the end of it. And
right.
What are you going to do? But you look at what it takes to pull billions of people out of poverty. We have it so well here, it's amazing. But look how much energy and how much raw material it takes to bring the life that we have. And if you thought about, well, wouldn't it be nice if billions of other people could have that? You come back to this great need for energy, this great need for raw material that is very difficult to do on Earth alone.
Yeah, totally. Yeah, people don't really, yeah, exactly. So a lot of people are watching this, students, engineers, or early stage founders who care about electromagnetic launch, mass drivers in general. If this conversation clicks with them, what's the most useful way they can plug in? What kind of talent, experiments, or partnerships would actually help move the needle for you or for mass drivers?
Well, first of all, anybody who would like to reach out to us can certainly do that. The website at electromagneticlaunch.com has more information and stuff to look at, but there's also info at Electromagnetic Launch, and we'll get the emails, and we're interested in more talent and that kind of thing. We have conversations already going with some folks from at a government level in terms of their funding and helping and support this, and same on the investment side. But, if there's somebody who's interested on that, they can also reach out. I would dearly love it, quite honestly, if somebody could. We've made quite an effort to reach out both to Elon Musk and Jeff Bezos. They're the kind of folks that can both afford an early TRL type project and recognize the long-term benefit of it. So if anybody could help get an introduction with one of those two, that would be a wonderful thing.
Are you interested in like electrical engineers, mechanical, or just all across the board?
All across the board. There's all kinds of mechanical engineering problems, electrical engineering problems. When we made the decision to disclose, because we lost a year or two really thinking that it was not right. There were strategic implications, and there's all kinds of background stories with having to do with international stuff, that when we finally made the decision to go ahead and disclose, this is how we're doing it, and this is why it will work. It's just a solenoid, but you just turn it off as you go. We kind of recognize that what we're really doing is telling people how to build and play a guitar. And if I gave you the complete video and this is how you should build and play a guitar, well, you already know how to play guitar. The truth of the matter is the secret is in the practice and the effort and the details. For those electrical engineers, for those mechanical engineers, for all of this work that still is yet to come, that may or may not end up being patented, may end up being trade secret and that kind of thing. But we need all of that kind of talent.
Right. That makes sense. Yeah, that's the case in a lot of industries. There's like these, I don't even know if they're nuances. They're just like, I guess nuances is the closest word, but yeah, like you said, it's the practice, it's the on the ground experience with these things. And when you're doing something completely new, there's like a lot of hurdles that, and unforeseen obstacles and just crazy things that happen that you have to figure out. So that's why it's, yeah.
If anybody's thinking about it from a career standpoint and all that, what I'll say is it seems probable that our future is in Florida, Central Florida. There's a number of reasons for that. Part of it is that the state of Florida would like to be helpful, I think. The state of Florida has the view that from an economics perspective, they've got tourism and agriculture pretty well nailed down, and they would like to improve where they're at from a high-tech perspective. And it happens that the United States National Magnet Laboratory is in Tallahassee. And of course, everybody knows about the Space Coast. So it is a ripe area for us from the standpoint of the talent and the people and the economy. So if somebody said they were really interested in this, but they couldn't be in Florida, I'm not sure that we would be a good fit. But that does look like where we're headed.
Awesome. And there's, you mentioned y'all are working with a superconductor, I guess, organization, or I guess if you want to talk a little bit about y'all's partners, if you want to.
Well, we have we have a bunch of partners, but the one that you're thinking about is a place called Magnetics Corporation. A guy named Jeff Whalen is the founder and the CEO, and was one of the physicists at the National Mag Lab in Tallahassee, and went off on his own entrepreneurial way, and MagCorp now builds superconducting magnets for other folks, medical things, and there's a whole range of needs for that technology. But he's one of our owners and a partner, and basically our relationship is we as the architects, they as the builders would actually build our subscale demonstrator for us.
Awesome. So yeah, it's great to hear that y'all have like these partnerships and connections with the exact kind of people that have navigated these sorts of industrial nuances, especially in this field.
We have the team to go build it right now.
Awesome. Yeah, that's pretty confidence inspiring. What qualities do you look for people that make them stand out as someone you'd want to work with?
Passion. In a previous life, I was a CEO for a lot of years, and then finally became chairman and had to hire my own replacement. And I'd put passion at the top of the list. But I'll tell you what else. Somebody who's just a good guy or a woman. Talented jerks are just, maybe there's something you can do on your own in life, but all of the stuff that I've ever been involved in, and certainly this, it's a team sport. So a talented jerk is basically the last thing you need. But if you take somebody who's got passion, and you take somebody who's really just a good person, and then honesty, without that, forget it. Those are the kind of attributes that you're looking for. And then finally, I think we're a sucker for smarts. We've always been that. There's some amazingly bright folks out of Caltech and MIT and out of all these great universities, smarter than I'll ever be. But folks that are like that are what we're looking for. This is a really cool project. I think we're going to be able to recruit the talent that we're wanting.
Yeah, I think y'all will attract a lot of attention. I'm hopeful that y'all will. And if I was graduating, I would be definitely probably applying at y'all.
Well, and Ian, I appreciate what you're doing. You're taking the discussion to a level. I bet a lot of your audience notices this. It makes me nuts when I'll see something on public TV or about, I'm interested in that subject, and you watch, and it goes like 1% into it. And then as soon as like a math formula is required or an understanding of how electrons are or some other kind of thing that's a little more detailed, they stop. Because their audience just isn't going to want that. And you've taken the kind of discussion that we just had to a deeper level from a technical standpoint. And, turns out there's a big audience for that. So I'm glad you're doing what you're doing.
Well, I appreciate that. And I'm very much looking forward to seeing some more holes and metal plates. From
We're not going to make any of those.
So I know a lot of young people are probably going to watch this. What advice would you give to young people today? Just in general.
I don't know that I'm qualified to give any young people advice. I mean, all the stuff that comes to mind are all the things that you're going to hear from everybody else, about life being short and all that kind of stuff. And it is. But if you can work on something that you're passionate about, that's really a good thing. It's really fun. And most people don't get that chance. Most people, have to. Ray Kroc said you have to be able to see the beauty in a burger, and that's true. So most people don't get a chance to work on something that's really cool.
Yeah.
But if you can, that's a great thing. So
I like that. The beauty in a burger. I can appreciate that.
It turns out for 99% of your audience who won't be working for NASA and won't be working on, our electromagnetic launcher or whatever, you really can. It doesn't, because what you're doing is you're working with people, right? It's not the burger. It's the people around serving the burgers or figuring out how to make the burgers better. Or, if it's wholesale plumbing, but it's the people around the project of how to do the wholesaling more accurately, lower cost, having a little bit of fun along the way with trying to be working really hard at doing it well. I don't know if that's advice, but that's what I've observed.
Right. Just appreciate the moment, people around you, and try to do something cool with your short life. I would call that advice.
All right.
At least something to appreciate.
All right. It's worth what you're paying.
Exactly. Is there anything I haven't asked you today that you'd like to mention?
No, I think we've covered a lot of ground. It's pretty interesting, and I hope to talk to you again down the road.
Yeah, I definitely appreciate it. I think this is a good conversation. I'm honored that you would talk to me today. So,
all right.
I'm excited.
You're quite
Very
welcome.
excited. Yeah.
Thanks very much.
Thank you.